Could we really travel to exoplanets suitable for human life? Let's cut to the chase. Today's topic is interstellar travel, specifically moving from one star system to another. According to official NASA data, on August 25, 2012, the cosmic radiation detector on Voyager 1 indicated that it had successfully left the heliosphere, stepping beyond the protection of solar wind and officially entering interstellar space. This marks humanity's first venture into interstellar territory. The data on Voyager 1 and 2 shows that Voyager 1 is currently moving at nearly 17 kilometers per second. Converting that to kilometers per hour, by multiplying by 3,600, we get a speed of over 60,000 kilometers per hour. In astronomy, speeds are often measured in kilometer per second. For instance, the speed of light is 300,000 kilometers per second. If we assume that Voyager 1 is headed toward Proxima Centauri b, the closest exoplanet to our solar system, how long would it take to get there at this speed? The answer is 74,473 years. That's an incredibly long time. This led to the concept of generation ships among scientists and science fiction writers alike. The idea is to put hundreds of people on a ship where they will reproduce over time until they eventually reach their destination. However, over the course of 74,000 years and assuming a 30-year generational cycle, we'd need to sustain 2,500 generations. That's a lot of human drama packed into one spaceship, to say the least. This leads us to today's question. Could we realistically reach an exoplanet like Proxima Centauri b, which is 4.22 light-years away, or the newly discovered super-Earth, 31 light-years away, or even Kepler 452b located 1,400 light-years away? The answer is yes, it's theoretically possible. Do you remember the 2009 blockbuster film, Avatar? The story is set on Pandora, a moon of a gas giant located 4.37 light-years away from the solar system. How did the protagonist travel from Earth to Pandora? The movie details a hypothetical interstellar spaceship and how it travels between Earth and Pandora. The ship accelerated at 1.5 grams for about 5.5 months to reach 70% of the speed of light, maintained this speed for 5.83 years, and then decelerated for another 5.5 months at 1.5 grams before reaching Pandora. The two phases of acceleration and deceleration are symmetrical. The film also introduced the concept of time dilation. Due to the ship reaching speeds of 0.7 times the speed of light, according to Einstein's theory of relativity, the passengers on the ship would experience time dilation. While 6.75 years would pass on Earth, just over 5 years would pass on the ship. In terms of time dilation as per relativity, for two inertial systems moving relative to each other, their perception of time would differ. As you accelerate to higher speeds on your interstellar spaceship, your perception of time would slow down. However, from your perspective, 1 second remains 1 second. 1 day remains 1 day. Only the duration of the journey shortens. Let's assume that in the world of Avatar, the starship is designed to travel at 0.7 times the speed of light. In that case, its time dilation factor is 0.7141. This means that the time experienced on the starship is only 71.4% of that in the Earth's reference frame. In simpler terms, if you travel at 0.7 times the speed of light for 10 years, from the Earth's perspective, 10 years would have passed, but for you, the traveler, only just over 7 years would have elapsed. When your speed reaches 0.14 times the speed of light, your perceived journey time decreases by 1%. This is why we say that if you haven't reached 0.1 times the speed of light, the effects of time dilation are negligible. If you could somehow reach 99.9996247% of the speed of light, your time dilation factor would be 1/365th. In other words, 1 day for you would equate to 1 year on Earth. Under the influence of time dilation, we can reach further distances in a shorter time. So, how fast do we need to go? Let's set up a new coordinate system. The x-axis represents the distance to the destination in light years, and the y-axis represents the time needed in Earth years. Using Pandora from Avatar as an example, it's 4.37 light-years away from us. According to the official data, It takes about 6.7 Earth years to reach there, but the traveler only experiences just over 5 years. There are two crucial variables: d, which is the distance in light years, and k, which represents the speed as a multiple of c, the speed of light. By adjusting these two variables, we can calculate both Earth time and traveler time to reach any destination. Let's be bold and set our destination as Kepler 452b, which is 1,400 light-years away. If we travel at 0.73 times the speed of light, we would need 1,311.33 years. Clearly, that's not feasible. We would need to bump up our maximum speed to 99.98% of the speed of light to make the journey in 29.26 years, though 1,401 years would pass on Earth. As of now, the fastest a human-made vehicle has traveled is 11.08 kilometers per second, set by Apollo 10 in May 1969. That's nearly 40,000 kilometers per hour. This record still stands, not because our technology hasn't advanced, but because this speed is close to Earth's escape velocity of 11.2 kilometers per second. So, if you were to build a vehicle faster than Apollo, you'd end up leaving Earth and never returning. Velocity is relative. When discussing interstellar travel, what should be our point of reference? We might naturally think of the Sun, but is that truly accurate? Apollo 10's velocity relative to the Sun is around 31.8 kilometers per second when Earth's orbital speed of about 29.78 kilometers per second is considered. When we talk about the fastest man-made objects, let's not consider crewed spacecraft for a moment. Instead, let's talk about the Parker Solar Probe. Launched in August 2018, it's expected to reach its maximum speed relative to the Sun by 2024, almost 200 kilometers per second. This is the highest speed any man-made spacecraft has achieved, according to NASA. You might think that's impressively fast, but let's talk about Voyager 1 for a second. Although its speed relative to the Sun is just 17 kilometers per second, it has actually achieved the fastest speed ever relative to human efforts. Why do I say that? Because speed relative to the Sun isn't necessarily meaningful. You see, the Parker Solar Probe was sent to study the Sun. To get closer to the Sun, it has actually been decelerating since its launch. From 2018 to 2024, it will use Venus for 7 gravitational assists to slow down. Ultimately, it will reach its maximum speed at its closest point to the Sun, about 6 million kilometers from the Sun's surface. This high speed is actually achieved by slowing down, which makes the discussion about interstellar travel and speed somewhat meaningless. Many of you may know that Earth's third cosmic velocity, or the escape speed from the entire solar system, is 42 kilometers per second. However, this velocity varies for different planets in the solar system. When you plot the planets, they all align on a curve determined by the mass of the Sun and the distance of the object from it. Why study this escape curve? Consider Apollo missions. Their speed relative to the Sun was about 31.775 kilometers per second, but unfortunately, that's not enough to leave the solar system. The Parker Solar Probe, although moving at 200 kilometers per second, is too close to the Sun. To escape the solar system from that position, it would need to be going at 452.6 kilometers per second. According to NASA, it will never return to Earth and will eventually plunge into the Sun. Finally, let's look at Voyager 1. It's far away, about 21.7 billion kilometers from the Sun, which is roughly 145 astronomical units. It has truly escaped the solar system, making it the fastest and farthest in terms of interstellar travel. In summary, it's theoretically possible to reach exoplanets tens or even hundreds of light-years away within a human lifetime, but the key lies in achieving the necessary speed or having advanced technology. Currently, the fastest interstellar speed humans have achieved is Voyager 1's 17 kilometers per second, which is about 0.0057% of the speed of light. This is a good start, but it far exceeds the limits of current rocket propulsion technology. We all know that rocket propulsion alone won't take us out of the solar system. What we rely on is gravitational assists. Many of you might have heard of gravitational slingshots, but do you really understand them? Or ion drives, controlled nuclear fusion, antimatter propulsion, or even warp drives capable of hundreds of times the speed of light. We'll discuss these technologies in the next episode.